Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a naive-based classifier. Even before I proceed to demonstrate how to build a naive-based classifier, may I request you to subscribe to my channel, also like and share my videos. Let me begin by introducing you to the data set that I'll be working on. As you can see here, this is the data set which I'll be working on. The name of the data set is called as Iris data set. This data set has 6 important variables. One is flower ID. The second variable is sepal length of the flower. Next variable is sepal width, which is measured in centimeter. Then you have petal length and petal width. I want to use these flower characteristics as the input variables. So sepal length, sepal width, petal length, and petal width. These 4 variables I will be using as the input variables. The dependent variable is species of the flower. If you look at the first record, the first record represents a flower whose sepal length is 5.1 centimeter. The sepal width here is 3.5. The petal length is 1.4 centimeter. The petal width here is 0.2 centimeter. This species of flower is setosa. What is the sample size in this particular data set? If I scroll to the last record, you can see here the sample size is 150. Let me scroll up. Now, one of the important points here is that let me apply the filter on the row header. Once I apply the filter here, you can see here for the target variable, there are 3 different species of flowers, namely setosa, versicolor, and virginica. I repeat, there are 3 different species of flowers, namely setosa, versicolor, and virginica. This kind of a problem, wherein the target variable has more than 2 groups, is called as a multi-class problem. I repeat, this is a typical example of a multi-class problem. Usually we have only 2 groups in the dependent variable, which would be called as a binary class problem. In this case, since the dependent variable has more than 2 groups, you can go ahead and call this as a multi-class problem. This point is very important because naive-based classifier works very well for a multi-class problem. In fact, whenever the dependent variable has more than 2 groups, one of the most effective and efficient algorithms that you can go ahead and use is naive-based algorithm. Secondly, in this data set, the sample size is very small, which is only 150. Given that we have a small sample size, naive-based classifier can be used because naive-based classifier is very useful for small sample sizes. So these are the 2 important advantages of using the naive-based classifier, because it works very well for a multi-class problem, and number 2, it works very well because it can handle extremely small data sets. With this introduction, let me now go to the next sheet. As you can see here, in the next sheet, you have important points about the naive-based algorithm. The first point that I'd like to talk about is the features of the naive-based algorithm. There are many important features of the naive-based algorithm. The first point here is naive-based algorithm is a classification algorithm. I repeat, naive-based algorithm is a classification algorithm. The second point here is that naive-based algorithm is suitable for both binary as well as multi-class problem. I repeat, it is suitable for both binary as well as multi-class problems. But we prefer naive-based when we have a multi-class problem because it is very effective and efficient in handling multi-class situations. The third point here is that naive-based algorithm performs well when the independent variables are categorical in nature as compared to numeric variables. With this, let me go ahead and answer a simple question as to what exactly is a naive Bayes classifier. When we say naive Bayes classifier, naive Bayes classifiers are a collection of classification algorithms based on the Bayes theorem. I repeat, naive Bayes algorithms are a collection of classification algorithms which work on the foundation of the Bayes theorem. It is not one single algorithm, but a family of algorithms where all the algorithms have a common principle. What is this common principle? This common principle amongst all the members of the naive Bayes family is that they assume that the independent variables are uncorrelated, or in other words, the input variables are independent of each other. So if you take any pair of input variables, naive Bayes algorithm assumes that these two input variables are independent of each other. Let me now go on to tell you some of the important advantages of a naive Bayes algorithm. The first important advantage of a naive Bayes algorithm is that it is very fast and simple. The second important point here is that it is very efficient in dealing with multi-class problem. The third important point here is that naive Bayes algorithm delivers high performance under two circumstances. First, when the input variables are independent, and secondly, when the input variables are categorical. As I've mentioned earlier, whenever the input variables are numeric, the performance of the naive Bayes algorithm goes down. Let's now look at some of the disadvantages of the naive Bayes algorithm. One of the biggest drawbacks of the naive Bayes algorithm is that we make the assumption of independence for the input variables. This is a dangerous assumption to make because while in theory, the input variables might be independent, but when you look at real life data, the input variables usually are not independent. Secondly, naive Bayes algorithm can be called as a lousy estimator. Typically, when you use Python after building the naive Bayes classifier, we use what is called as predict_proba. The output of predict_proba is not completely reliable. It should be taken with a pinch of salt. The last point here is the problem of zero frequency. Now, this is a very important point. What do I mean when I say the problem of zero frequency? Let me go ahead and explain this. If your test data set has a categorical variable of a category that wasn't present in the training data set, the naive Bayes model will assign it zero probability and won't be able to make any predictions in this regard. This phenomena is called as zero frequency, and we'll have to use a smoothing technique to solve this problem. Let me now move on to the applications of the naive Bayes algorithm. One of the biggest application of naive Bayes algorithm is in dealing with multi-class problem. I like to stress this point again and again that when it comes to multi-class problem, naive Bayes is one of the most popular and effective techniques. Secondly, it is used for spam filtering. It is used mainly for classification of web pages as well as email classification. Gmail uses naive Bayes algorithm for the classification of web pages. Thirdly, we can use naive Bayes for sentiment analysis. Based on a comment, we can identify whether a particular comment is positive sentiment or negative sentiment. If the tone is positive, we can classify it as positive, else we can go ahead and call it as negative. So here again, for sentiment analysis, naive-Bayes algorithm is one of the most preferred algorithms. Last but not the least, for recommendation system, especially in e-commerce websites, naive-Bayes along with collaborative filtering is widely used to make recommendation to the customers. So these are some of the important applications of naive-Bayes algorithm. To summarize this particular discussion, remember, a naive-Bayes algorithm is not one single algorithm, it's a family of algorithms. The main advantage of a naive-Bayes algorithm is that it works very, very well for small data sets. Secondly, it works very, very well for multi-class problem. And thirdly, one of the most important assumptions that we make while using naive-Bayes algorithm is the assumption of independence for the input variables. With this background, what I'm going to do now is to proceed to show you how to build a simple naive-Bayes classifier for the iris dataset. I will be using the dataset which is called as iris. The name of this software is called as StatCraft P. This is a very popular software. It's a Make in India initiative. There are multiple variables. I've already loaded the source dataset into StatCraft P. This is the dataset. If I click on this particular option, you can see here there are approximately 150 cases which we will be utilizing as the input for modeling. How do we build a naive-Bayes classifier? To build a naive-Bayes classifier, let me first click on the analysis tab. What StatCraft does is it displays the menu which allows us to build different models. I will go over to the option which is called as machine learning. Under this section, you have different machine learning algorithms. Let me now click on the drop-down menu. As I scroll down, you can see here MLP classifier, MLP regressor, decision tree classifier. I'll ignore all of these things. One of the last options here is called as naive-Bayes classifier. Since I want to build a naive-Bayes model, let me go ahead and choose this particular option. In the last iteration, I had specified some of these options. So what I'm going to do is simply choose refresh. Usually, the moment you hit the naive-Bayes option, this is the window that StatCraft displays. Here, I have to specify the dependent variable as well as the set of independent variables. The dependent variable here would be the variable species. And when it comes to the independent variables, I can choose the flower characteristics like sepal length, sepal width, petal length, and petal width. One of the biggest advantages here is that I have a multi-class problem. However, the biggest disadvantage in this case is that all the 4 independent variables that I'm using would be numeric variable. None of these variables are categorical variables. Remember, a naive-Bayes algorithm works best when the input variable is categorical in nature. Whenever the input variables are categorical in nature, naive-Bayes delivers better performance. I'll choose the options tab. You can see here, 75% of the data will be used for training. The remaining 25% will be used for testing the data set. We can look at the prior probabilities. StatCraft would use its own value to set the prior probabilities. Now, let me choose the option save. Here, since I want to use the predicted probabilities, and the predicted probabilities. Sorry, predicted values and predicted probabilities. I stand corrected, my apologies. The first option that I'll click is predicted values, and the second option that I'll choose is predicted probabilities. Choosing these two items would create two new variables in the data set. What are these two variables? One is the predicted value of flower species, and the second one is predicted probability associated with this. You can see here, these are the selections that I've made in the data set. Once you've made these selections, what you can now do is you can simply hit the OK button. StatCraft takes a couple of moments to process the analysis. You can see here, this is a new window. This window is called as the output window. In the output window, you can see the output of the algorithm that we have run. You can see here under the naive-based classifier, StatCraft firstly gives you the Python code. This is very, very important because there is no other software that I know of that gives you the backend code that it is using to execute a particular algorithm. You may ask me, what is the advantage of this? The biggest advantage of this is you can copy this particular code and paste it in Jupyter Notebook and rerun the analysis. You can make modifications to the input variables if you choose to. I'll ignore this point as of now. Let's look at some of the important output that StatCraft gives me. Firstly, the class count. You can look at Setosa. The count would be 34. For versicolor, it is 42. And for Virginica, it is 36. Let's look at the prior probabilities. For Setosa, the prior probability that is used is 0.30. For versicolor, the prior probability is 0.37. And for Virginica, it is 0.32. Let me scroll further down. Now, this table is called as the variance table. You can see here, along the rows, I have got the 4 independent variables. And along the column, what do I have? I have the 3 species of flower. Let's look at sepal length. You can see here, for Setosa, it is 0.10. The value of the variance is 0.10. For versicolor, it is 0.26. And for Virginica, it is the highest, which is 0.35. This simply means that the value of variance for the variable sepal length is the highest for the Virginica species of flower, which means that there is more dispersion in the Virginica species when you use the variable sepal length as compared to the other 2 flower species. Let's examine the sepal width. In this particular row, the value under Setosa is 0.15. For versicolor, it is 0.09. And for Virginica, it is 0.08. The highest value here is for Setosa species. What does this mean? This means that Setosa species of flowers shows the highest value of variation in sepal width. The same interpretation can be made for petal length as well as petal width. For petal characteristics, the largest value is 0.28 and 0.07. Both of them is for Virginica. So for petal characteristics, the highest value of dispersion is observed in the Virginica species of flower. Let me scroll down. What you're seeing here is the means table. I've got 4 variables here. Let's now look at sepal length. Let's compare the 3 numbers. You can clearly see here, Virginica has the highest mean value for sepal length, which is 6.5 centimeter. So when you look at this value, what you can say is the largest sepal length corresponds to Virginica species of flower, and the smallest sepal length represents Setosa. Let me look at the second row, 3.42. this is the highest value. It simply means that when you look at petal width, setosa flowers are the ones which have a large mean value for sepal width. Now, let's look at petal length as well as petal width. For the petal characteristics, clearly you can see here the largest value is 5.5 and 2.04. So if you're using petal characteristics, clearly the average value of petal length and the average value of petal width is more for virginica. So large petal length and large petal width corresponds to virginica flowers. Now, to evaluate the performance of the model, we look at what is called as the confusion matrix. You can see here, this is the confusion matrix for the training data set. Along the row, you see the observed category, and along the column, you see the predicted category. The diagonal elements here represent the correct classification. The off-diagonal elements here represent the misclassification. For example, when you look at setosa, the row is setosa and the column value is also, my apologies, the column value is also setosa. What does this mean? There were 34 setosa flowers, and these 34 setosa flowers have been correctly predicted as setosa. I'll repeat this. There were 34 setosa flowers, and all of these 34 setosa flowers have been correctly predicted as setosa by the naive-Bayes classifier. Let's look at the second diagonal element, which is 40. You can also see here 2 here. So 40 plus 2 would be 42. Out of the 42 versicolor flowers, 40 of them have been correctly predicted as versicolor. 2 have been misclassified as virginica. Finally, when you look at the number 34, you can add this with 2 here. So let's look at the row total, 36. So there are 36 virginica flowers. Out of these 36 virginica flowers, 34 of them have been correctly predicted as virginica. So this tells me something about the quality of the model. I do not have too many misclassifications, which is a clear sign that the model performance is on the higher side. But remember, this is only for the training data set. You can make similar interpretation for the test data set as well. So what you're seeing here is the confusion matrix for test. So for setosa, we are getting wonderful results. 16 out of 16 setosa flowers have been correctly predicted. Please look at the number 8. This simply tells me that 8 out of 8 versicolor flowers have been correctly identified in the test dataset. For virginica flowers, out of 14, 12 have been correctly identified. 2 have been misclassified as versicolor. So these numbers are very, very promising. These numbers are really good. Now, let me scroll down. What you're seeing right now is the overall classification report. The first one is for the training data set. Now, when we look at the training data set, there are important metrics here like precision, recall, and F1 score. These diagnostic measures are used to tell the quality of the model. What is precision? How is precision calculated? Precision is simply the ratio of true positives divided by true positives plus false positives. If you have a precision value of greater than 0.7, it is a very good sign. And for the virginica class of flowers, you can see here the precision value is 0.94. What does this imply? Precision has a very interesting relationship with the false positives. A high precision value indicates low false positives. So since we have a very high value of precision, this indicates that for Virginica flowers, there are very few false positives. You can make the same argument for recall as well, except for the fact that in the case of recall, the formula is true positives divided by true positives plus false negatives. So in the denominator, you have the sum of true positives and false negatives. Recall has an inverse relationship. Recall has an inverse relationship with that of false negatives, imply that as the false negatives go down, recall goes up. So we have a very high recall value of 0.94, which is greater than 0.7, indicating that the false negatives in our model is less, right? Only if the false negatives go down, the recall value goes up. So these are good indications. We have a good precision value. We also have a very good recall value. Finally, what we have is the F1 score of 0.94. Again, what is F1 score? F1 score is nothing but the harmonic mean of precision and recall. 2 times precision multiplied by recall divided by precision plus recall. I repeat, 2 times precision times recall divided by precision plus recall would give you the F1 score. So 2 PR divided by P plus R. Here again, you can see here, we have a very high value of F1 score, indicating that for Virginica, the performance of the model is good. You can similarly look at precision, recall, as well as F1 score for Setosa flowers. It is 1, which means that we've been able to get all of these right. You can also look at the values of precision, recall, and the F1 score for versicolor. All of them are greater than 0.7, indicating that we have a very good model. Now, what I'm going to do is scroll down. You can now look at the classification report for the test dataset. Again, for the test dataset, you can see high value of precision, recall, and F1 score for Virginica, which means that for Virginica flowers, our model is performing very well. The same argument can be made for Setosa. It is 1. The precision value is 1. Recall is 1. And F1 score is also 1, which means it's almost 100%. So for Setosa, our model is performing very, very well. Let's now look at versicolor. It is 0.8, 1, and 0.88. These are the values of precision, recall, and F1 score under the test data for versicolor, which is again very, very promising. So this clearly shows that the naive-Bayes model that we have built has done a very good job in predicting a multi-class problem. The performance of the model is really good. If you want to look at the predicted values, I can click on the view button. And after clicking on the view button, what I will do now is go on to data. Earlier, you had information till species. You can now see 2 new columns being generated. One is the predicted value. Predicted by whom? Predicted by the naive-Bayes algorithm. You saw in the classification report that for Setosa flowers, our model was exceptionally good, which means we had obtained 100% accuracy. You can compare the actual and the predicted. The actual flower, at least the first 12 flowers that you see are all Setosa, and the predicted value is also Setosa, and the predicted probability here is 1, which means that with 100% probability, the naive-Bayes algorithm is able to classify Setosa as Setosa flower. Let me scroll down. So for Setosa, there is barely any misclassification. Let's now examine versicolor flowers. You can see here, this is the actual versicolor. This is the actual flower. This is the actual category for versicolor. and this is the predicted category. So the actual and the predicted are matching. Here, the naive Bayes algorithm is telling me that there is a 89% chance, there's an 89% probability that record number 51 will be a versicolor flower species. So most of the versicolor flowers have been again classified correctly. My first impression when I look at this is that you don't have too many misclassification. However, when you look at the 78th record, you can see here the actual category of species is versicolor, but the naive Bayes model has misclassified this as virginica. This is one glaring mistake. The rest of the cases more or less look okay. Let me now go on to the second page. You mostly have virginica flowers, and again, the actual is matching the predicted category. So most of these flowers, virginica flowers, have again been correctly classified. I see a misclassification here. You can see here, this is the 107th record. The actual species of flower is virginica, but the naive Bayes model has predicted this as versicolor. So this is clearly a misclassification. So you can see here that 134th case again seems to be a misclassification. This is a virginica flower predicted as versicolor. The next case, 135th case, is again a misclassification. A virginica flower has been misclassified as versicolor. So this is how you can generate the predicted values here as well as the predicted probabilities. With this, I have come to the end of today's video. In today's video, we have seen how to build a naive Bayes model. We have seen what exactly is a naive Bayes model, what are the important features of a naive Bayes model. We have seen the advantages, disadvantages, as well as the application of a naive Bayes model. Further, we went on to build a naive Bayes classifier to predict and classify the iris flowers. We obtained a very high level of accuracy. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much. Have a great day ahead.